to chapter 3 here. Hopefully it'll open up. So in chapter 3, we're going to talk about matter, different states of matter. We'll also talk a little bit about elements and compounds. We'll talk about mixtures, and that's about it. Physical and chemical changes as well. We'll talk about those. All right. So when we talk about matter, matter is basically anything that pretty much occupies space and has mass. That's pretty much everything. And a lot of what we deal with in chemistry is really the different sort of states of matter and it changing it from one state to the next. So we do have our solid state. And in our solid state, everybody is pretty much packed in there, pretty tight to one another. Not a lot of room for movement happening, not a lot of energy for movement. They're in there pretty close to one another. We also then have sort of the liquid state, where they're still relatively close to one another. But there is a little bit more room for movement, a little bit more energy. They're able to sort of pass each other. So when we think about things in the liquid state, they're fluid, right? We could pour them and they pour obviously like liquids. The last sort of state of matter that we commonly come across is gas. And in the gas state of matter, pretty much at that point, everybody has broken apart. So everybody's flying around in the container they're in. There's collisions that are occurring, which cause pressure, as we'll talk about when we do get to the gas chapter. So these are three very common states of matter. We deal a lot with chemistry, again, with sort of the transition from one state to the next. Also, a lot of times the energy required sometimes to do those transitions. So let's talk a little bit about what the names of those transitions are. As we go from solid to liquid, that is the process of take an ice cube out, it starts to melt. Yeah, so that's the process of melting. You feel bad about your ice cube melting, you take it back and you put it back into the freezer, going from liquid back to solid. That is the process of freezing. Going from liquid to gas, that is the process of evaporation or vaporization. And going from gas back to liquid, if you cool down the gas, that is going to go into the liquid state, and that is what is known as condensation. There's also a process where we go from solid directly to gas, and we skip the whole liquid mess, and that is the process known as sublimation. There's also a process where you can actually go from gas back to solid, once again, skipping the liquid part. That is what is known as deposition, like you're depositing something. You might be familiar with sublimation. If you've ever seen dry ice, dry ice goes from solid directly to gas, skips the whole liquid cleanup. By the way, dry ice is actually carbon dioxide, it's not water. I guess they maybe still sell these things like DVDs and CDs. How they get really shiny up on top. That's how they do a process of deposition to put the metals up on there. Now, when we talk about these sort of transitions of state, which is a very common thing that we do look at, and we'll look a little closer in some other chapters, when we have the process of melting and freezing, does that occur at the different temperatures or same temperatures? What do you think? Melting and freezing actually does occur at the same temperature. So for example, something like water, it's 0 degrees Celsius when that occurs. So it actually does occur at the same temperature. Sometimes referred to as the melting point or freezing point of a substance. So for example, for water at 0 degrees Celsius, you basically have both phases sort of happening at the same time, like ice crystals. So you got some solid, you got a little bit of liquid. It's not until you get above 0 degrees Celsius that you really have all liquid, and not till you're below 0 degrees Celsius for the case of water that you actually have ice. Same thing over here. Evaporation and vaporization and condensation really does occur also at the same temperature. And that is what is usually sometimes referred to as the normal boiling point of a substance. So for example, water as well, that's 100 degrees Celsius where water will boil. And that's when it will go from really liquid to gas. Again, same deal at exactly 100 degrees Celsius. You basically have both things happening. You have liquid and you have sort of water vapor, if you will, or steam. Not until you get above 100 degrees Celsius, again, in the case of water, you really sort of water vapor or steam, and not until you have less than 100 degrees that you have liquid water. That's what happens really at the all liquid. There's this sort of constant exchange. Guys going into the gas phase, guys coming back into the liquid phase. That's why things, as we'll talk about in a later chapter, evaporates, right? If you have a little bit of water or something on the bench, right, it will eventually evaporate because you have a rate of evaporation happening greater than condensation. Now, another major thing that we look at when we think about matter and the different states of matter is energy associated with it. And that's actually the next chapter we're going to talk about. But in terms of energy, as we go from solid to liquid to gas, do I need to put energy in to do that? Or do I need to take energy out to do that? What do you think? So if you have a ice cube and it starts to melt, are you putting energy into the ice cube or taking it out? In. You got to put energy in. The ice cube picks up all the energy from the surroundings, right? Or if you want to speed up the process, you could heat it, right? And it will start to melt. If you have liquid water, right, and you start heating it, putting energy in to the water, it will start to boil, right? And you can make pasta and all that good stuff. So these going through solid to liquid to gas, that's all processes where energy is actually absorbed by the system. And those type of processes are what are referred to as being endothermic. So an endothermic process is one where heated energy is basically being absorbed, and that is what's happening in those cases. And it is the opposite as we head the other way, as we go from gas back to liquid, back to solid. As we have gas molecules flying around, basically we need to remove energy from them. As they lose energy, they no longer have enough energy when they come in contact with other gas molecules enough to escape. So they kind of clump together and drop into the liquid, if you will. You continue to remove energy, like put it in the freezer, they will continue to come together because they no longer have enough energy to really move at all. And they go into the solid state. So that process going from gas to liquid to solid, that's all where energy is released. And that is what is sometimes referred to as an exothermic process. Any questions on that there? Okay. So matter, as I mentioned, again, basically has those two important characteristics, has mass and occupies space. Solid, obviously things like wood or bone. Solid things are very rigid. They have a definite shape and they're very difficult to change. So clearly, this here, our tabletop, I can't easily fold it up or anything like that. It is solid. It's very hard to change its shape. Liquid, on the other hand, things like water or gas, they do not have a definite shape, but they do take the shape of whatever container you put it in. But they also do have a definite volume. And what that means is, I took like 10 milliliters of water and I put it into a cup, it would take obviously the shape of the cup. If I poured that water into the trash can, it would take the shape of the trash can. Put in one of those silly straws, right? It'll take the shape of that. A definite volume means, though, if you started with 10 milliliters and you just kind of moved it from one place to the next and you're not a klutz and spilled it all over the place, you should still have 10 milliliters as you move it from one sort of container to the next. On the other hand, for example, air. By the way, the major component of air is what element? Nitrogen. That's actually the major component of air, followed by oxygen, and a bunch of other stuff depending on what air you're breathing. But air is a gas, and most gases take the shape of their container that they're in, and they fill it uniformly. So the idea behind gas molecules are basically they're flying around. So as they're flying around, they're pretty much completely filling the volume of the container they're in. As we'll talk about in terms of the gas chapter, the idea of something that's an ideal gas is that we actually don't actually look at the volume of the gas itself, but we actually look at the volume of the container it's in, because the idea is it's flying around perfectly, kind of filling the entire container. So that's oftentimes what we look at. Any questions on that there? All right, so here's obviously some pictures of liquids and the different shapes that they could take. Now, we talked a little bit about water, I think the other time. Water, again here, which is H2O, right? Looks something like this. Water in its solid state, basically when the water molecules come together, actually, again, is less dense than water in its liquid state. And the reason for that is, as you can kind of see in this picture, when the water molecules actually lose enough energy and come together and they start to hydrogen bond with each other, it creates all this open space between the different water molecules. So they can't get fully tight to each other like most things in a solid state. And if you think about density, like we talked about, density is mass divided by volume. So because there's all this empty space, it bloats the volume, and that would mean that the volume would be a larger number, the density would be a smaller number. So that's why the density of ice is less than liquid water. Again, most things, as we talked about, in their solid state are actually more dense than in their liquid state. In the liquid state, water isn't as sort of more close to that. It still has enough energy to keep moving around. So they actually can get closer to each other, but they sort of lose that ability as it goes into the solid state, kind of spreads out and gets a little bit bloated. Obviously, steam here, our water molecules would basically be flying around. Now, what affects things like how we would determine whether or not, or make a pretty good educated guess as to, would this thing maybe be a solid under normal conditions? Would it be a liquid or a gas under normal conditions? Really, the major thing that determines things like melting points and freezing points and boiling points, whether they're going to be really high or really low, atoms interact with each other. One major thing that helps us determine whether or not something maybe will be a gas versus a solid is what is referred to as an intermolecular force. And basically, an intermolecular force is how one molecule basically interacts with another. Now, for something like water, what happens is one water molecule basically binds to another. And most intermolecular forces basically use this idea of opposites attract. So in chemistry, much like in life, opposites attract. So positive and negative thing are attracted to each other. If you are two positive people, right, you don't want to be around them. That's just too cheerful. Two negative people as well don't want to be around each other. So things that have the same charge actually repel each other. So what happens in the case of water, water actually is more negative on the oxygen part, more positive on the hydrogen part. So they're able to really come together and bind through hydrogen bonding. And that's a relatively strong sort of intermolecular force. And that's why water has a pretty high boiling point of, say, something like 100 degrees Celsius. That means under normal conditions is going to be most likely a liquid, maybe a solid, probably will not be a gas. If you take something else like, say, methane, which is CH4, that's basically the stuff that comes out of your gas vent when you light your Bunsen burner. It has a very weak intermolecular force. And because of that, when a couple of like methane molecules get together, it really doesn't take a lot of convincing for them to basically get away from each other. So things with really, and that's why obviously methane is a gas. So things with really strong intermolecular forces, how they interact with each molecule, if they have a really strong attractive force to one another, that would usually result in a much higher melting point and boiling point. And if things have a very weak sort of interaction with itself, like something like methane, it's going to result in a much lower melting point and freezing point or boiling point. And that usually would be more in a gas phase. Any questions on that? And we'll talk more about that in a later chapter as well. So this table is from your book. You have a similar table. And again, it just goes over some of the stuff that we talked about. Solid, obviously, having the fixed shape and rigid, definite volume, but takes the shape of the container for the liquid, and no fixed volume or shape, but really does take the shape of its container, the gas phase. Let's then talk a little bit about physical properties and physical changes and chemical properties and chemical changes. A physical property can basically be measured without changing the composition or identity of the substance. Very common physical type properties are things like color, volume. The state of matter, like we've been talking about, is a solid, is a liquid, is a gas. Things like density, melting points, and boiling points are all sort of typical physical properties. When we talk about physical properties, it also goes about with the idea of a physical change. And important with a physical change is pretty much this idea of what you start with and what you end with are fundamentally the same thing. So for example, if we take our ice cube example, and I heat it up and I melt it to liquid water, the difference between ice and liquid water is this state of matter, right? One's solid, one's liquid. They are both fundamentally the exact same thing. They're both H2O. So molecularly, it hasn't changed. It hasn't gone under any type of chemical reaction to occur. It is still water, it just looks differently. If you have a peanut and you crush it into a bunch of small little pieces, it's still a peanut, right? It just looks different. Fundamentally, it didn't change, into a strawberry or anything like that. It is still a peanut. Fundamentally, what you started with and what you ended with are exactly the same thing. If you have a shirt that's really wrinkled and you iron it, it's just not wrinkled anymore, right? But it's still a shirt. So these are all sort of examples of physical changes. You have a board here, right? And I color it red. It's still a board, right? It didn't fundamentally change to something else, like paper or anything like that. It's still fundamentally the same thing. So that's the important part about a physical change. Again, whatever you start with and whatever you end with is fundamentally the same thing. It may just, again, maybe look different and maybe in a different state. Common physical changes are really those changes of state going from solid to liquid to gas. Any question on physical changes? So that's the example of the ice there. Again, once again, it is all H2O, really no difference in the actual composition of what it is made of. Now, different than that are chemical properties and chemical changes. A chemical property is one that describes sort of the ability are the resistance of a substance to go through really a chemical reaction. So most chemical properties usually happen during a chemical change. And in a chemical change, it's a little different than a physical. What you start with and what you end with are fundamentally different. So what you actually begin with, it actually goes through a chemical reaction or a chemical change, and it turns into something different. Rusting of steel is an example of that. Rust happens when you have iron, metal, and a little bit of oxygen gas and a little bit of moisture is pretty much all you need. Oxygen and the iron come together and make iron 3 oxide, which is basically rust. At that point, the iron and the oxygen are chemically united. If you ever had something that was rusty, you could do whatever you want to it. You'll never get the oxygen gas back. You'll never get the iron back by itself. If you do any type of physical means like boil it, freeze it, whatever it may be, filter it, you're not going to get those guys back. It has fundamentally changed from iron by itself and oxygen by itself to those two guys together that makes a new compound. So that is an example of a chemical change. If you take some hydrogen gas and a little bit of oxygen gas, you can make some water. That is a chemical change that occurs. We know that once it makes water, which is a new substance, you can heat the water, you can freeze the water, you will not get the hydrogen gas or oxygen gas back. Otherwise, if you were boiling water and you got hydrogen gas and oxygen gas back, you would never make it to the pasta part where you put it into the water because it probably would explode. So you could heat it all day, it will never get back to those things. The only way that you could get back the hydrogen and the oxygen is actually you'd have to do another chemical change or chemical reaction to it, which you'll do in a future experiment. You could take some water, run an electrical current over it, and it will break into hydrogen gas and oxygen gas in this case. So that again is an example of a chemical change that's happening going the opposite way. Once again, you can take the hydrogen and the oxygen, take the hydrogen and freeze it and stuff like that. You will not get the water back unless you react those guys back together. So chemical change, what you start with and what you end with are two fundamentally different things. And really, you cannot get back the original substances by any type of physical means. Any questions on that? There's the hydrogen gas example. Also, for example, you know, if you made a hard-boiled egg, there's a lot of chemical changes on, and any type of food that we eat, right, goes into our body. Enzymes, proteins, all those kind of things break it down into other chemicals, right, and changes of things, which are chemical changes that occur. So summary of physical and chemical changes. Once again, physical change, one or more physical properties change, but no fundamental difference in terms of what you started with to what you end with. Again, as I mentioned, really the most common type of physical change that we see a lot in chemistry is the changes of state. A chemical change definitely involves something changing, a chemical reaction occurring. What you start with and what you end up with are fundamentally two different things. For example, if silver tarnishes, basically any type of metal that tarnishes, go through oxidation, those are all chemical changes that are occurring. Basically, that piece of metal and oxygen reacting with each other. You know, so as you do in terms of physical changes and chemical changes, you know, is whatever you did to the object or whatever it may be, before and after, is it really just the exact same thing? Did it look like nothing really changed? You know, did it go back to what it was before? Or did you do something where when you pulled it out, maybe of the fire, there was some change that actually occurred to the object? Did something actually grow on it, or not where it grows, the right word, but does something kind of find itself on it? And that would maybe be an example of a chemical change. Other common examples of chemical changes are really chemical reactions, or things like bubbles, right? Bubbles indicate that a gas has been made. So some type of generation of bubbles that occur is an indication that gases have been generated, and that probably means you didn't have a gas to start with, so you made something new. That would be a chemical change. If you mix things together and you get a solid that forms, that's sometimes referred to as a precipitate. That's an example of a reaction that took place. And really sort of the oxidation part is also an example of chemical changes that occur. Any questions on the differences between physical and chemical changes? So let's talk a little bit about elements. Elements are basically as far back as you could go. So there's obviously the periodic table up there on the wall, and the periodic table has basically all of our elements listed. The basic unit of an element is an atom, and an atom has protons, electrons, most of them, and neutrons, most of them. And we'll talk more about atoms in a sort of later chapter, but the basic sort of unit of any element is the atom. And elements can be monoatomic or they can be diatomic. There are certain elements like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They actually come as what is referred to as diatomic molecules. That is how these guys naturally come by themselves when they're uncombined. They basically come as tubes. So like hydrogen, there's two hydrogen atoms bonded together. Oxygen is a couple of oxygen atoms bonded together. That is how they come. A lot of them are gases, like hydrogen, nitrogen, oxygen, fluorine, chlorine. They're gases. Bromine, iodine, they're sort of liquids and vapors. That's how they kind of naturally come. By the way, all other elements, they're on the periodic table. They come as what is referred to as being monoatomic, basically one atom. So outside of these guys, which you should know, that is how they come. Everybody else on the periodic table there, all the other elements come as monoatomic, which means they just come as ones. The other sort of misconception also a little bit about the periodic table is if you have an element by itself, not combined with anybody else, they have no charge. So things do not have charges unless they actually start combining together. So if you had a piece of zinc metal like you're going to have today, copper metal, they do not have charges by themselves. It only gets charges when things really combine. So everybody on the periodic table has no charge. There are some elements that come as actually molecules. So what is the definition of a molecule? A molecule is basically just the combination of two or more atoms. So when somebody says a molecule, it's really, you can think of it like a basic definition of I got at least two or more atoms together. Now those atoms could be of the same element, which would still make them a molecule, or they could be different elements, which would make them actually a compound. So it doesn't really matter as long as you have two or more atoms, same element, different elements, it is considered a molecule as one type of classification. So for example, in terms of H2, O2, and so forth, these guys are all elements because they're only made up of obviously one element. So H2 has two hydrogens, O2 has two oxygens, they're considered elements. But because they are actually made up of two atoms or more, they are also considered molecules. So these are a molecule of H2 and a molecule of O2. Now, if you have something like water, which is H2O, H2O is basically, as I drew earlier, 2 hydrogens and 1 oxygen together. This is also a molecule because it has atoms of 2 or more elements together, or 2 or more, sorry, it's a molecule because it has atoms of 2 or more together. In this case, though, it's a hydrogen atom, oxygen atom that's involved. It would not be an element because it has 2 different elements involved. But this thing would also be classified, though, as a compound, which a compound is 2 or more atoms of different elements. So if you have a combination of 2 or more atoms of different elements, it's considered a compound. It would also be considered a molecule. Would water be considered an element? No, again, because it has hydrogen and oxygen involved. Would H2 and O2 be considered a compound? It would not, because it has 2 atoms, but they're 2 atoms of the same element. So that's why they're considered elements. So again, in order to be a compound, you have to have different elements, 2 or more atoms. In order to be a molecule, you just simply need to have 2 or more atoms. So there's sometimes people get confused about molecules and compounds, which one's which. Any question on that? Yeah. No, I said H2 and O2. H2O2 would be what then? It would be hydrogen peroxide. And would it be a molecule? It would be a molecule. It's got definitely more than 2 atoms involved, so it would be a molecule. Would it be a compound? It would be a compound. If I could spell all that badly up here. Would it be an element? Would not be an element, again, because there's hydrogen and oxygen, so 2 different elements, so it can't be an element. So this is a molecule. It is a compound, but again, it would not be an element. Other questions? Speaking of that, before we go too far, let's talk a little bit about the periodic table. Just quickly, periodic table, on most periodic tables, right around boron, which is kind of in this area, there's usually like a staircase that kind of comes down. You kind of see it up there, a kind of dark line going down from boron. And there's usually 2 rows at the bottom as well. So usually everybody to the left of that staircase, and even these 2 rows down here, those are usually elements that are considered metals. Metals are good conductors of heat and electricity. They're usually shiny as well. And those are some characteristics of metals. Kind of above the staircase in sort of this region, that is what is referred to as nonmetals. And nonmetals basically have the opposite. They're bad conductors of heat and electricity. They're also dull, they're brittle, and so forth. Kind of where the staircase is coming through here, that's a group of elements which are considered metalloids, or semi-metals. And much like sort of their location, they're sort of in the middle between metals and non-metals. So the metalloids have properties that are very similar to metals, and the same guy also has properties that are very similar to non-metals, like semiconductors and stuff like that. So the metalloids sort of have properties that fall kind of on both sides, and that sort of makes sense as to where they're at. So we'll talk more about the periodic table a little bit later in another chapter, but there might have been a question or two on the post lab maybe about metals and non-metals. Any questions on that? So as I mentioned before, again, compounds has to have 2 or more different elements involved in order for something to be a compound. Compounds, again, are as far back as you could go. So through a chemical change, chemical means you can definitely break a compound back into its elements, but that is as far as you could go. You cannot break it any further than into their elements. So for example, as we talked about just a second ago, and you'll do that in an experiment, you'll take some liquid water, you'll run an electrical current over it, you'll get some hydrogen gas and oxygen gas to bubble out of there. You'll actually see the bubbles occur. And again, bubbles, an indication that gas has been generated. And again, also an indication that you probably had a chemical reaction occur because you weren't bubbling before you did anything. So as it starts to bubble, some type of chemical reaction took place. Now, the properties of compounds are usually very different than the actual elements that make it up. So clearly, the properties of water are very different than the properties of hydrogen gas and oxygen gas. Clearly, water is mostly a liquid. It's not a gas. It's not very toxic or flammable water, but hydrogen gas, oxygen gas is. And you'll light one on fire today, perhaps in lab, and it'll make some sound. So they can ignite. And obviously that's very, very different. Also something like sodium metal, which is a nice soft metal, and chlorine gas, which is a nice green toxic gas. You probably wouldn't want to eat any of those things, but when they do come together, they do make sodium chloride, a little bit of salt, which, put on our fries and stuff like that through the miracle of chemistry won't kill us, but definitely wouldn't want to put sodium metal or chlorine gas on your fries. Probably wouldn't taste so good, and you wouldn't be so good afterwards as well. So very, very different properties when things come together, actually make bonds and compounds, than the actual elements that make them up. Any questions on that there? So let's then talk about mixtures and pure substances. A pure substance is really any form of matter that you pretty much just have one thing. So that is definitely a pure substance. So for example, if you just had water by itself, that is a pure substance. And since we were talking about it, some sodium chloride or salt by itself, that would also be a pure substance. So if you take together two or more pure substances and put them together, you get what are referred to as a mixture. So if I were to put this together, I would get a mixture basically of salt water when it comes together. So a mixture is a combination of two or more pure substances that are put together. And the main part of that is they still retain their identity. So nothing changes. They just mix together. It may appear to you that something has changed, something has went away, something disappeared, but they actually do retain their identity and they're still there. Because they retain their identity and they're still there, when you make a mixture, is that a physical change or a chemical change? It is a physical change, yeah. You know this because of the experiment maybe you did on Monday, right? You took the salt in the water, the salt dissolved. That is a mixture between the salt and the water, right? The salt is actually still there. You threw some sand in there as well. You mixed it together. It didn't really dissolve the sand, but it was still there. So that's a different type of mixture. And you were able to filter out the sand, right? So you got the sand back. You were able to heat up the liquid and get the salt back. So these things still retain their identity, even though in something like salt water, it looks like, the salt's completely gone. Maybe it reacted away. It really didn't. It is still there. So it is a physical change, and that's an important part of it. There are two types of mixtures. One is a homogeneous mixture. And in a homogeneous mixture, that's pretty much our salt water example. With sufficient mixing, when you mix it, everything does mix together. Everything looks the same throughout, like the salt water. So if you looked at the salt water, or if you ever drank some just water from the ocean, nothing else is floating around in the ocean. It just looks like water, right? Until you taste it and go, wow, that's pretty salty. So you can't tell the salt's in there, but it definitely is in there. Same thing with sugar. If you took some sugar and you put it into some water, the sugar would dissolve and you wouldn't be able to see it. It looks just like water, like the same throughout. So in a homogeneous mixture, you don't, everything mixes nice and it all looks like one thing. Different than that is a heterogeneous mixture. In a heterogeneous mixture, when you mix it, even with sufficient mixing, you'd still see different layers or different phases. So the sand's an example of that. Maybe you mix really hard with the sand and it never dissolved, I hope, unless you have special sand, but the sand shouldn't have dissolved when you did that. You could clearly still see the sand in the water. That is a heterogeneous mixture. If you took some metal pieces and you threw it into some sand, you would still see the metal pieces in the sand. So that definitely is a heterogeneous mixture. The best heterogeneous mixture, the chocolate chip cookie, you still see the chocolate chips if you do it right in the cookie, right? So that definitely is a mixture where you see different phases and stuff like that. So regardless though of the type of mixture, regardless of whether it's a homogeneous mixture or a heterogeneous mixture, you could still do some type of physical means to separate them out and really get back your original substances in kind of their normal form or original form. So for example, you did a couple of these things the other day. One really good way to separate out a solid from a liquid is the process of filtration. So much like you kind of did the other day, you take like a nice funnel, artsy funnel there, put a little filter paper on there, maybe something to catch. And if you took your sand and water mixture, which obviously is a heterogeneous mixture, as you can still see the sand in there, and you put it in there, the liquid water goes through, right? And the sand ends up there on the filter paper. You take the filter paper out, let the sand dry really good. You got your sand the way it originally was. And obviously you have your liquid water the way it originally was. So that's a really good way to separate those things by physical means. So filtration, obviously a physical process. Now, when you look at something like what you were left with here, or in your experiment, not really in that picture, but in your experiment, you could do something like distillation, which is a good way to separate out a homogeneous mixture. So for example, if we took something like salt water, which obviously is a homogeneous mixture, and we set up sort of distillation apparatus, looks something really wonderfully drawn like this, kind of a closed container. I know I failed art 9 times, it's okay. And we keep the kind of tube connects the two sides of those wonderfully drawn flasks, really, really cold. And if we put our salt water on one side and we start heating it, when we start heating the salt water, what's going to happen to the water part? It will start to evaporate, right? And as it evaporates, it's got nowhere to go, which means it's going to go through that really cold tube. When we have gas and we cool it back down and take energy out, it goes from gas phase to the liquid phase. It goes through condensation, and it will actually start to drip out on this side. And if you continue to heat this, eventually all your water will evaporate away and you'll be left with salt on that side. So by that process of distillation, we actually collected the water back from what we started with, and we actually collected the salt back as well in its original form. Similar to what you did on the experiment the other day, except that you use an evaporating dish. And in the case of the evaporating dish, the water just evaporated off into the air, right? We didn't capture it or anything like that, but as you continue to heat it, what you had left in your evaporating dish was the salt part, much like you're going to do today as well. You're going to basically evaporate off the water. You have some crystal-ish, or probably like a smear color like that at the bottom of your evaporating dish. You're going to evaporate off the water. We're not going to collect the water in this case, but we could if we wanted to. So these are two very common ways to separate out a mixture. Again, regardless if it is a heterogeneous mixture or a homogeneous mixture. Any questions on that there? Now, when we talk about dissolving something, look at something like salt water, and you think to yourself, well, where does the salt go? And I know it's there when it comes back. So how does that all work? When you have something like sodium chloride, which is a salt, it really is two ions together. It's a positive sodium ion and a chloride ion that has a negative charge. And when you take something like water, which is a polar molecule, and we'll talk about in a later chapter as well, again, the hydrogen part of water is more positive. The oxygen part is more negative. So when you have an ionic solid, it's basically sitting together like this. A bunch of those ions are basically clumped together because it has a very, very strong attractive force. That positive negative attraction is pretty much the strongest forces you could have. So with nothing else there, it just sucks them together. This nice solid. So what happens when we go to dissolve something, the sodium ion that goes into the solution actually gets surrounded by a bunch of water molecules. And it's actually the oxygen side of water that surrounds it, because that's the negative side of water. And when the chloride goes in, it's actually water's hydrogen side that surrounds it. And there is lots and lots of water molecules that basically come in and grab out those ions. And those basically prevent the really strong attractive force between the sodium and the chloride to come back together to make the solid. So what happens though, right, when we put this in our evaporating dish like you did the other day and you heat it up, as we heat it up, we start to evaporate off the water molecules. And as you continue to heat, there's no more water molecules. And now there really is no barrier to prevent those guys from coming back together. So that's why your salt reappears after you heat it up. Basically, you got rid of all the water that was getting in the way and allowed those ions to come back together, remake that solid ionic compound like it was when you took it out of the little jar where you scooped it out. And it was that white solid. It allows it to come back together. Question on that? Yeah. How do I know if, which one? I'm sorry. We'll talk about it in a later chapter, but typically speaking, metals end up being positive and non-metals end up being negative, but we'll talk about it actually in a later chapter. Now, we also help this process along, right? So typically when you go to dissolve something, you do what? You start to stir it, right? So as you're stirring it, you're doing two things. You're adding more energy, and you're also throwing a bunch of water molecules all over that solid. So it's going to allow a lot more interaction to occur and allow those ions basically to separate out and actually dissolve. Any questions on that? So sometimes people think, well, the thing disappeared, so clearly it had to be a chemical reaction that occurred, but it's not. Again, this is all a physical change that occurred. All right, so there's a much prettier picture of distillation. Look just like mine if you close your eyes. But once again here, the salt water here, as you heat it, water evaporates, and then we're just left with the salt and the water. Again, physical means to separate those guys out. Any questions on physical changes, chemical changes, mixtures, elements, compounds? All right, that wraps up chapter 3. We're actually going to go to chapter 10 now, actually. Just give me a second to get it. Up to chapter 10, so obviously we're going to skip a couple of chapters. We're going to come back to them, obviously, afterwards. So we did 1, 2, 3, off to 10. 10 is all about energy. So we're going to talk about different types of energy in this chapter. We're going to talk about specific heat and some enthalpy, which are, again, ways to represent energy. Exothermic, endothermic sort of processes a little bit more as well. So let's get into it. First off, when we talk about sort of energy and changes in energy, it really is, as we will see, what is sometimes referred to as the first law of thermodynamics, which is the law of conservation of energy. Which means energy is neither created nor destroyed. One thing when we think about energy in chemistry is it's really sort of a perfect exchange of energy. When I created nor destroyed, energy can be transferred from one place to the next. And when energy gets transferred, we think about it as sort of a nice complete transfer. And what that means is whoever, say, loses a certain amount of energy, somebody else has to gain the exact same amount of energy. So there's sort of a constant exchange of energy that occurs. And one way that we represent sort of where energy is going and maybe coming from is through the system and the surroundings. So when we talk about the system is really anything in the universe that you're interested in. So when you do experiments in your test tubes or your beakers, that is your system. Everything outside of the system is known as the surroundings. So there's the system and the surroundings. Sometimes energy travels from the system to the surroundings. Sometimes it goes from the surroundings to the system. But again, it's sort of an equal flow of that energy. And whatever one gains, the other one will lose. So again, when we talk about sort of our system and our surroundings, we could have energy flow out of the system to the surroundings, or again, have the surroundings actually flow some energy into the system. An example of the surroundings flowing energy into the system, if you don't do anything to it. Yeah, because from the surroundings, the ice cube is picking up all the energy, right? And it's going to start to melt. So, those things can happen. There's three types of systems that we oftentimes deal with. One is an open system. In an open system, you basically can have exchange of mass and energy with the surroundings. In a closed system, the energy can exchange, but mass cannot, so you can't take anything out. And in an isolated system, we have no transfer of mass or energy. I would say for most of the time you work in open systems, like in your test tubes, you could take stuff in and out, right? If you hold on to the test tube, you could feel it get hot or cold. By the way, if I'm holding onto a test tube and it feels hot, energy is being released from the reaction, right, into your hand. And if you hold the test tube and it feels cold, energy is being absorbed from your hand to the test tube, which means you'll feel that coldness. So here's an example of some of those things. Most of the time, open systems, a lot of times what we deal with, sometimes closed systems as well. So when we talk about energy, energy is really the capacity to do work or change. So since energy can be measured, energy is basically force times distance. There are different types of energy that we come across and just found around. Chemical energy, there's actually energy stored within the structural units of compounds. So for example, if I were to make a bond, a chemical bond, would I need to put energy in to make the bond or take energy out to make the bond? What do you think? So actually, when we make a bond, we actually have to remove energy. So if you think about it, you got two things that are moving around like this. As it loses energy, they kind of slow down, and that allows them to come together to make the bond. So actually, when we make bonds, it's actually a process where energy is actually being released. And when we release energy, once again, that is what is referred to as an exothermic process. And opposite of that, if we do have a bond and we want to break that bond, energy is actually absorbed in that case. So if you think about it, you got a bond and it starts to absorb energy. Everybody gains enough energy to kind of wiggle away from each other and the bond can break. And again, any process that sort of absorbs energy is an endothermic process. As we'll also talk about in this chapter, just overall processes, in addition to making and breaking bonds, which is typically what happens in a chemical reaction, there's sometimes a net difference of sort of all the energy of the reactants to the products, and sometimes the reaction overall gives off energy to the surroundings. Again, kind of like if you're holding a test tube and it starts to feel hot to you. Somewhere the reaction does need to absorb some energy from the surroundings. So again, like if you're holding that test tube, it starts to feel cool to you. Potential energy is another type of energy. It's the energy based on its position. That is the classic example of the big giant boulder about ready to fall off the cliff. Hopefully there's nobody below it. It can then be turned into kinetic energy as it falls over the cliff, right? Turns into some kinetic energy, and then it splatters on the ground. Once again, hopefully nobody's standing there. As it hits the ground, it's going to transfer the energy to the ground, right? And it will end up at a lower potential energy. Again, there's a conservation of energy that occurs in this process. The difference between the energy here and here of the big boulder would be transferred obviously to the ground and so forth. And that would be our kinetic energy. So once again, that law of conservation of energy, we don't create energy, nor do we destroy it, but it definitely can be transformed into one form or another. Any questions on that there? Now, thermodynamics is sort of what we talk about when we're talking about the law of conservation of energy. That is actually the first law of thermodynamics. If you continue on to Chem 1B, you'll talk about the second law and the rest of thermodynamics, and you'll also talk about conservation of energy in 1A one more time. But the idea of thermodynamics just in general is this idea. It really is used a lot of times to help us determine whether or not a reaction is going to be spontaneous. And sometimes people have a misconception about the word spontaneous when it involves a chemical reaction. They think spontaneous and they think snap your fingers, it's like done in a second. And that's really not what spontaneous means when we're talking about thermodynamics. Spontaneous just basically means under these conditions, this reaction should actually take place. It could be really fast, it could be really slow. There's a lot of spontaneous reactions that are like super slow that you got to kind of speed them up if you want it to be anything of value to you. But again, sometimes people think spontaneous, it's got to be fast. Another topic that you'll talk about in 1B that actually deals with how fast or slow a reaction takes place is what is known as chemical kinetics. So kinetics deals with the speed of a reaction, but thermodynamics really tries to answer a lot of times that simple question of, whether or not this reaction under these conditions should take place regardless, either fast or slow. It's just going to hopefully take place. There are certain functions which are known as state functions. State functions basically are determined solely by two major things: where you start and where you finish. That's basically the only two important things about a state function. Things like energy is a state function, pressure, volume, temperature. So if we look at this diagram here, both hikers started at the bottom. The blue guy took the direct route up the hill. The red guy took the scenic route up the hill, but they both are now currently standing basically in the same position. So they have the same potential energy. The only thing that's important is where they started and where they finished. That's why in a lot of cases, when we calculate the change in something, we take the final conditions minus the initial conditions. Final conditions where we ended, initial conditions where we started, and change of energy, pressure, volume, temperature. Those are all things that we final, and ending is the only thing. Another thing that we'll talk about in this chapter a little bit is the idea that not all chemical reactions take place in like a one-step move. They don't all start at the beginning and go to the end in one move. It may take a lot of individual reactions to get you to the end result. And it really doesn't matter in terms of things like energy. It could take you like 4 reactions to get to the end. It could take you 2. The only thing that's important is where you started and where you ended. When we think about chemical reactions, we basically have reactants, which is our starting material. And we have products, which is our ending material. So as we will see in this chapter and maybe some other sort of chapters, a lot of times when we do calculate energy, we basically will add up all the energy of our products and we'll subtract it from all the energy of our reactants. So that's basically our final state minus our initial state. And that's a very common sort of calculation that we do with energy. So this is basically our final, and that's our initial. Any questions on that? So there are some important units associated with energy. And here are some, not too many people use Newton meters anymore, which is what that is. Most of the time, energy is usually in joules or kilojoules, which is 1,000 joules. Also, a little calorie, little c, or kilocalories is also another very common unit of energy that we come across. Actually, 1 joule, as we see here, is equal to a kilogram meter squared second squared. That's actually these are all no negatives here. It's just PowerPoint, but that's actually a good conversion. We come across it, I think, maybe once down the road, but in 1A and 1B, you come across that kind of conversion a lot, and helps you make sure you use the right units. But a joule is equal to a kilogram meter squared over second squared. There's 1,000 joules in a kilojoule, and that is the conversion between calories and joules. 1 calorie is 4.184 joules. That is definitely something you should know. That number pops up a lot, especially in this chapter and as you continue on, for sure. What is a calorie? A calorie is basically the energy that's required to change 1 gram of a substance or 1 gram of water by 1 degree Celsius. And that is basically what a calorie is. Now, there is another type of calorie that we sometimes come across, which is a nutritional calorie. And for exaggerated purposes, I'll write it like that. It has a capital C. So when you see a capital C for a calorie, that's actually a nutritional calorie. That actually equals 1,000 of the little calories. And that equals 1 kilocalorie. So nutritional calories, we'll talk a little bit about as well in this chapter, like on your nutrition labels on your food and stuff like that. You know how many calories you burn at the gym. Those are all nutritional calories, which again is the capital C, and that is equivalent to 1,000 of the little guys, which is the amount of energy required to raise the water by 1 gram, 1 gram of water by 1 degree Celsius. Any questions on that? Now, thermal energy and temperature, there is sort of a difference between the two. Thermal energy is really the energy associated with the random motion of molecules and atoms. So you would have greater thermal energy when you have more atoms and molecules that are there, although the temperature is a measure of kind of the change in energy. So for example, if I had a big bathtub full of water and it's only 40 degrees, and I had a coffee cup, that's 90 degrees. The one with more thermal energy is which one? It's actually the bath of water. The bath of water has much, much more molecules and atoms in it than your little coffee cup. Your little coffee cup has more temperature, right? It's hotter. And that's because your coffee cup is a much smaller spot, right? And the energy is given off there. It's going to raise that temperature a lot more than it would take to raise a giant bathtub of water to the same temperature, right? So in terms of temperature, is a measure of sort of energy, but thermal energy is based on how many molecules and particles there are. The greater the thermal energy. Even though the temperature may say something higher, something else may have more thermal energy. So they're not exactly the same thing. Thermal energy. And that is basically what we just talked about there. And although the coffee cup has a higher temperature, there is much, much more energy stored in because there's a lot greater volume of molecules in there. So let's talk a little bit about heat here and officially exothermic and endothermic processes. By the way, heat flows from cold to hot or hot to cold? Yeah, it goes from hot to cold. So the hot guy cools down, right? The warm guy picks up the energy, kind of cools up, or cools up, I guess, warms up, and they will meet somewhere in the middle, you know, if they're in an insulated container. So heat is really defined as the flow of energy due to some type of temperature difference, or transfer of thermal energy between two bodies that are indifferent. We've talked about exothermic processes. Those are processes where, again, heated energy is released like striking a match. Again, you could feel the heat and energy coming off that. Endothermic processes are when heat and energy is absorbed. And again, kind of like the test tube, if you held it was cold, or the ice cube melting. There's a couple of common ways that we display heat in chemistry, and how we could kind of tell just from sort of the energy value if something is exothermic or endothermic. One common way that we kind of deal with heat is what is known as delta H, and that is the change in enthalpy. And it's really the heat of a reaction. So it's really the heat of reaction. And if you have a delta H value that is negative, that usually indicates that that reaction is an exothermic reaction. We would expect energy to be given off. Doesn't really matter the number. It's actually just a sign. So if you see negative, exothermic being given off. If you have a delta H value that ends up being positive, that is usually an indication that an endothermic process is occurring. Energy is being absorbed. So it's a very common way in chemistry that we sort of deal with energy. Another one that we're going to talk about in this chapter is Q, which is heat. And it's kind of the same thing. If you end up with a Q value that is negative, that is going to be an exothermic process. And if you end up with a Q value that is positive, that will be an endothermic process. So in general, if you're doing anything that is sort of a energy or heat value, and it's a positive number, that should tell you automatically probably dealing with an endothermic process. Energy is being absorbed. If you end up with a delta H or a heat value that's negative, it should tell you overall that process is most likely going to be exothermic, and heat and energy would be given off. Any questions on that? All right, it's a good place to lay it up, I think.